Hello, and welcome everyone to our webinar, Faster Steady-State Results in MEMS Simulation with Harmonic Balance. First of all, very happy to see so many of you registered for our event here. And as a reminder, all of the registrants will indeed be receiving the recording of this event and the executive summary PDF within 1 or 2 days from here. So, to introduce myself, my name is Jukka Knutinen, and I'm the head of marketing here at Quanscient, where we have a cloud-based FEM multiphysics simulation software called Quanscient Allsolve we'll be using in today's demonstrations. So today, in the next 60 minutes, we're going to go over the harmonic balance method, specifically in MEMS simulations. We'll start with the fundamentals, what it is, how it works, how it differs from transient analysis, and move all the way up to how it can be utilized in real-world use cases to achieve faster simulation runtimes and a much more straightforward setup. Our technical speakers for today are our CTO and co-founder, Dr. Alexander Halbach, and the team lead of our application engineering team, Dr. Abhishek Deshmukh. Now, before passing the mic on to Dr. Halbach to give straight into the main topic itself, I want to very quickly give some context on who we are as a company and how our product is tied to the topic of the day. So as said, we're Quanscient, a company based in Tampere, Finland, and we have a cloud-based multiphysics simulation software called Quanscient Allsolve. Now, based on the participant list, I can already see that many of you are likely familiar with the software, but for the folks who haven't heard from us yet, let's do a quick rundown of the key features and capabilities. So first and foremost, Allsolve is a natively cloud-based tool, meaning that it has been designed from the ground up to take the full advantage of cloud computing in practice, resulting in the ability to handle much more complex models with faster runtimes and capabilities for a practically unlimited number of parallel runs, for example, with zero added computational time. So in essence, removing the computational bottlenecks in simulation work. Next, with Allsolve, there is an unlimited number of licenses with every plan. So in other words, there are no licenses. So just simply when an organization purchases a plan, anyone can have access and add it as a user and use the software. Also, as the software is fully browser-based, there are no hardware requirements, and doing a project, for example, is quite literally as easy as sharing a link. Now, something our users like a lot, which we'll actually see today, is the Python scripting interface, which for one is automatically generated while you set up your models, and also is very easily accessed and modified in the GUI. So for teams with knowledge in Python, this really allows for flexibility that you won't get elsewhere. Then I think that the pricing is usage-based, meaning that there won't be license sitting idle, and also the number of licenses will be a bottleneck. And finally, our application engineers really do go above and beyond when it comes to guaranteeing the success of our customers' projects. We, of course, have documentation, tutorial videos, user guides we're updating weekly. So all in all, just as context, Quanscient Allsolve is quite a powerful, very flexible simulation solution for organizations ranging from small startups all the way to these huge listed companies. But yeah, now that we have some context on what the software that today's demos will be presented on is all about, I'll give the stage to our CTO, Dr. Alexander Halbach, who will jump right into the topic of today. So Alex, please introduce yourself and tell us what we're here for.
Thank you, Jukka. Really nice to be here with you. So I'm Alexander Halbach. I'm CTO and co-founder at Quanscient. I did my PhD in computational electromagnetics in Liège in Belgium. And one other thing relevant for the MEMS talks we're going to have here today is that I was MEMS design engineer for 2 years at IMEC in Leuven. So let's start immediately with the topic, the harmonic balance method. So it's a, let's say, pretty unknown method for quite a lot of people. This actually solves a lot of problems that people are facing, and they don't even know that there's such a solution. Some of you I know are familiar with it, but I'll start with the basics. So for this, let's consider a very typical lump model of a micro device, a micro ultrasound transducer, for example, such as a CMOT, for example, where you apply a voltage across 2 electrodes. This creates an electrostatic force, and you have a restoring force that is here the K spring. You have a dashpot for the damping, and you measure the displacement versus voltage. This is not something that I'm going to show in simulation. I will show another one, very related, but just to explain what harmonic balance is. Now, this is a nonlinear problem because the electrostatic force is dependent on the square of the voltage, and as the membrane moves up and down, the electric field strength increases or decreases. Now, if you apply a voltage here, DC bias plus an AC oscillation that is small around, what you will see is that you have two parts of the response. You have first a transient where the brutally applied DC leads to like a lot of vibration, and these vibrations are damped over time. And after some time, you enter what's called a steady state, where you have still a DC voltage bias applied, and you apply your small sine AC on top. And what you end up with is a DC bias plus a sine vibration. And there are these typical two parts, transient and steady state. And the topic today is, what if you're interested in the steady state, but you don't want to go through the transient, you want to get the steady state immediately. Now, if it's a linear problem, that's trivial. You do a harmonic frequency analysis. But if it's a nonlinear problem like here, then you have new harmonics that can appear, and you have to account for all these nonlinear effects. And this is where classical commercial software basically stop. And this is where we go further by extending this harmonic analysis in the nonlinear domain, where you can get all the frequencies in the Fourier domain in one go, as usual, without doing a transient analysis. The downside of doing this transient analysis is that typically for these MEMS ultrasound sensors, for example, the goal is that they have a really high Q factor in some cases. And so basically, this transient here is actually very optimistically short, but there are many applications where the transient takes forever. Like you have thousands or 10,000s of periods before you reach the steady state. And this is where it's absolutely impractical to do a transient analysis. You really want to do a nonlinear frequency analysis, which is the harmonic balance method. Additionally, you have a lot of you have more likelihood to have manual steps involved if you want to get the steady state, and you go through a transient analysis because you have to transient to the steady state. You have to a frequency analysis of the response at the end. So this is more likely to involve manual steps for the user, more time consuming to set up. And also, of course, you never exactly reach steady state, so you also have noise on extracted frequency. So a lot of downsides here with actually not much or no upside at all to the transient analysis. Now, how does this work? Well, it's really not that complicated. The complicated part is that if you have a code base that it's written and it has been validated for tens of years, you have to change the code pretty much everywhere. And so you don't necessarily want to do this. Here, Allsolve in Quanscient has been written from the very beginning with harmonic balance in mind. So the way this works is that you split each field, and this works for any multiphysics simulation. We'll show here for 3 types of multiphysics simulations. You split each field in your simulation, for example, displacement, electric potential, fluid velocity, or whatever. You split it into a sum of sines and cosine in the Fourier space. So basically, any signal that is periodic splits like that. And so these Fourier coefficients, we call them harmonics. So if you look at the sine omega t, the omega is 2 pi f, and you have a driving frequency. This is what we call the fundamental frequency. Now you have a multiplier to this fundamental frequency because you have a nonlinear problem. When you drive with, let's say, 1 kilohertz, you might have 2 kilohertz, 3 or 10 kilohertz harmonics appearing because the system is nonlinear. You might also have DC components appearing, even though you drive things purely in an AC way. So if you set omega to 0, then the first term on the sine, that's always 0. That's not of any use. The cosine of 0, that's 1. And this actually shows the appearance of this phi C0, which we call harmonic 1. So harmonic 1 is the solution that's going to give you the constant component of your problem. Now, if you set in 2 pi ft, the omega to 2 pi f, then the sine, the coefficient of the sine 2 pi ft, is what we call harmonic 2. So it's the real part at the fundamental frequency. The cosine, it's the imaginary part at the fundamental frequency. And this is what we call harmonic 3. And then if you go at double the fundamental frequency, so what people usually call the second harmonic, then you have again a real and imaginary part, which is, in our case, harmonic 4 and 5, etc. So you can really have as many harmonics. And a nice thing also is that you can cherry pick the harmonics. So if you have modulation, so a frequency and a modulation frequency, you can really cherry pick around the carrier frequency and around the modulation frequency. So a lot of flexibility here also for problems with really different time scales. Let me show you one example about this. So the very simple lumped CMUT model with a mass damper spring, if you drive it with 10 volt DC and 1 volt AC, then you're in a linear regime. And what you're going to see then is basically it's the bottom part, which corresponds to the top part. So you see there is a static average minus 0.5 deflection, whatever the units. And you also have a swing around this of some amplitude. So that's you have two harmonics. So the C0 has the biggest intensity, and then the S1 has a smaller intensity, but then all the rest is pretty much zero. And basically here, what you see out in the response, it's just a linear behavior when you feed with two different frequencies as a supply, as a drive. So this is all linear. But now if we ramp the AC voltage to 10 volts, then you start to have nonlinear effects. And obviously here, the response doesn't look like a sine wave plus a DC anymore. Here you have to account for new harmonics appearing. You can see the C2 harmonic. Basically, this originates from the quadratic behavior of the electrostatic force. So when you feed with a sine wave, the square of the sine is a constant part plus sine at double the frequency, which is the harmonic C2, which we call harmonic 5. So clearly here, it's nonlinear because you feed a signal, a driving signal with 10 volt DC, 10 volt AC at a given frequency, and you get these, but also double the frequency as a response. So this is clearly a sign of a nonlinear behavior. And here you get the Fourier coefficient in one go with the harmonic balance. So the goal really with the harmonic balance method is to extract these Fourier coefficients. Now, what I will show now is the first and the most simple explanation of how this works in Allsolve in the product on a very simple, but actually not that simple problem if you really look at it. So it's AC Joule heating. So imagine you have an AC current, purely AC current. We will change the frequency. We'll see that in just a second. And I think it's just easier if I show it immediately in the product. So this is my, imagine I have a very tiny conductor piece here. So it's small so that it has the time to cool down and to heat up. This is why it's chosen small, but basically it's the size of, let's say, a copper wire, except here it has a square cross section. But what happens now in this wire, if you set up, so let me go through the setup first. We define a frequency that we will be able to use to make a frequency sweep. We set the material to some aluminum. We could use copper, of course, for a copper wire. We set up the physics. We define the current flow. So this is all the physics you can define here, and the harmonic balance is going to work on all of these. You set your constraint. We ground the right side of the cable to 0 volt, and then we inject a given current on the left side here by stating that the current drive is sine 2 pi ft with 1 amp peak. And we will see how things behave as you change the frequency. We also add the heat solid, so thermal conduction physics. We ground thermally the left side and right side to a reference 0 temperature. And then we add the multiphysics coupling Joule heating everywhere. So the Joule heating is nonlinear with respect to the currents. So it's the current density times the electric field. And this is a nonlinear behavior that we will just now analyze. If I solve this problem in the way that is usually done, then what I will get here, actually I could run this live. So I make a frequency sweep for this transient analysis. I will run for 200 hertz current drive, 400 hertz and 800 hertz. And what we will see is that you have a transient, as I just showed in the slide. And then And then basically for the higher frequency, you will see that the swing around a static heating is the lowest, and the higher the frequency, the lower the swing. But the lower the driving frequency, the longer the cable has to cool down, and so the higher the swing. If you want to know how much is the swing around the constant temperature, then, well, you can do a transient analysis, of course. In Allsolve, it's pretty nice. You can actually do several transient analysis at the same time. But still, it's a transient analysis. And if you want to know what's the swing value, it's not the most convenient way to do this. But so the alternative way to do this is actually to do the harmonic balance analysis. So what you do is that you use what we call multi-harmonics, the harmonic balance here. You select what's the harmonics that appear. Here we will have a constant part. Actually, we will have no component in the heat at the driving frequency. We will also have a component in the heating at double the driving frequency. And then you basically run, in this case, a frequency sweep from 1 to 501 hertz by 41 equidistant step. And what you're going to see is that, if I run it again, if you plot the maximum value of each harmonic, you will soon see just a second, they are arriving. So harmonic 1, 2, 3, 4, and 5. So now I just ran 41 runs at the same time. We get the whole curve. And what you can see is that you have the constant heating, which is on harmonic T1. It's this part. This is around 71 millikelvin, and this matches actually the steady state value that you get here and the transient resolution. So you can see that it kind of settles at something that is close to 70 millikelvin, and this matches very well. And you can also see that as the frequency increases, the swing around the static heating decreases actually. So the blue curve is the lowest frequency, and then this one is higher frequency, and even higher frequency, the swing obviously decreases. And this is also coded here. So the swing is this harmonic 2 in blue and 3 in red. So this is the swing. Actually, no, sorry, that's the 4 and 5. This is the swing at double the frequency. So you can see that you have a static heating in steady state, and this doesn't change with frequency in this case. But then the oscillation and the swing decreases as the frequency increases. And one other thing to notice is that it's 0 on harmonic 2 and 3, and on the harmonic 4 and 5, which is double the driving frequency. This is where you have actually the swing. And this you can see here. Here I'm just driving one period of AC current, and you can see that you have 2 oscillations for the heating. So obviously it's double the frequency, the swing around the static heating. Now, this is a very simple example. Like what I could show as well here is the script that is associated. So really compact script. As Yuka mentioned, we generate automatically the script, and you can see it's the multi-harmonic or harmonic balance method in action. So you can cherry pick exactly the harmonics you want for each different field. So this is for the electric potential field, and this is for the temperature field. And otherwise, the equations remain the same. It's just automatically treated by the software. Now, this concludes this very simple electrothermal heating part. What I could show next is the backbone curve. So this is another application now, and this is purely mechanical. So what do we have here? We have a clamped beam. And if you check the usual resonance peak of a clamped beam, then you have a resonance frequency, the first mode vibration, here around 162 hertz. And well, here there's some damping. So you can see, obviously, this is very usual. At the resonance frequency, you have the highest oscillation, and that's it. This is a linear regime problem. Now, if you check the same problem, but you include geometric nonlinearity, then you have something actually very different. You have a backbone curve. And this center of the peak is still at the same frequency. But the thing is that because of the geometric nonlinearity, there are 2 possible solutions for some frequency. There's the solution where the vibration is really tiny, and this is just the same as in the previous graph. But there's also the solution where the vibration is really bigger. And so because due to the geometric nonlinearity stiffening, it can still vibrate and resonate at that frequency because of the nonlinear behavior. Now we will explore this and we will see how that works in Quanscient Allsolve. Now it is worth mentioning here that doing a transient analysis to get these curves is really tricky. And these curves actually occur in pretty much anything that vibrates. This applies to ultrasound transducers, but also to like turbo machines for aircraft engines. And I'm really sorry we don't cover this part. I know there are people in the audience who do just that. And we'd love to have a talk about this with you, but this part covers really more the MEMS part of the applications. But nevertheless, let me show you this backbone curve. So very simple case. This is inspired from a paper, nice paper written by someone in the audience. And what we have is simply solid mechanics. We have a beam, it's clamped. So you set up the clamp on the left and on the right. You set up a center point load, like at the center point that is visible here. And this load basically is just a sine wave with a given amplitude. You could also set here the large displacement. This would include immediately the geometric nonlinearity in the model without doing any scripting. But since we're going to do some scripting anyways, because we have to use continuation methods, I added it immediately in the script. So we can first run the linear regime. So what do you get in the linear regime? Well, let's run it again, just again to exemplify that you can run several things at the same time because it's running not on your desktop computer, but on the cloud. So you have pretty much unlimited amount of hardware and resources available. Yeah, so in one go, you can see all the jobs are starting and finishing pretty much at the same time. But this is a very simple linear resonance frequency simulation. But again, it highlights a bit the ability to run several frequencies at the same time. But now let's jump in actually the nonlinear behavior. So this is what you're going to get with if you take geometric nonlinearity into account. So you will have to run several simulations, or you will have to use continuation methods like it's used here to obtain the full curve, because obviously there are several solutions possible and you have to kind of get on the track to get on the right part of this curve. Now, the way this is done is actually very easy. This is the entire script for it. It's really as short as this. You pick your harmonics that you want to use. So here, the DC part, which is not active actually. The first fundamental frequency, double the fundamental frequency, and 3 times the fundamental frequency. And then what you do is, well, I edited a bit the script because we don't support for now continuation in the script just like that. So what I did was adding a while loop. So we defined the field, mechanical displacement field. You put a while loop. This was generated automatically by the script. And then I do some smart or not so smart continuation methods. Again, I don't want to compete with anyone in the audience. They're experts on this topic, but nevertheless, some kind of naive continuation methods. And the only thing that really is done here is that you have a field that is defined. You solve for your equations here. And then you go to the next iteration and the field state is used as it is. Just you don't have to do anything. It just happens naturally. And basically this provides already some sort of continuation method. But yes, quite easy to set up. The first example that I covered was really easy, fully graphical, very convenient. This one is more advanced, most graphical, but again, you might want to have the flexibility to do exactly what you want in the scripting interface. And now let's move on to the next level of difficulty. And for that, I will give the room to Abhishek.
Thank you. Just quickly before moving to Abhishek's demonstration, if you're not already following Quanscient on LinkedIn, I strongly encourage you to do so. We're almost 5,000 followers strong, And yeah, we keep you up to date with new features and overall advancements we're making in the field of physics simulation. So if stuff like that is of interest to you, which it likely is as you're attending this webinar, I strongly encourage you to consider giving our page a follow. But with that, I'll let our team lead of engineering, Dr. Abhishek Deshmukh, showcase what harmonic balance looks like in even more advanced applications. So the stage is yours, Abhishek.
Thanks, Yukka. Hello, I'm Abhishek Deshmukh. I'm team lead of application engineering at Quanscient. I did my PhD in multi-phase flows and turbulent combustion. And today we'll have a look at the more advanced example on harmonic balance. Um, yeah. So, uh, so the use case that I have chosen here is from this open access paper from 2021. It's based on the microspeaker, so newly emerging applications of MEMS, um, MEMS actuate or uh, electrostatically actuated MEMS devices. And yeah, so the microspeakers are one of them, which are silicon based and electrostatically actuated. The reason for going for this technology is to have a wider frequency range and also dynamic response of these speakers. And one of the challenges that these let's say these fabrication or even the operation of these MEMS actuated microspeakers is the instabilities, for example, pull-in instabilities and yeah, unstable equilibrium. Um, so in order to design these devices, one needs to perform some kind of simulations to gauge the response and um, response of the design. So let's move on to the setup. So in this case, the setup is quite simple. There are two parallel plates, which are separated by an air gap. One of the plate is fixed, and the top plate is able to move. Basically, it can deform in one direction, and as I said, so these are actuated by electrostatics, and this is done by applying a voltage on the top and uh, yeah, between the top and bottom plate. We will exploit some kind of symmetry on one of the sides here. So we will reduce the domain by half. Um, yeah, and in this case we'll use harmonic balance method as shown by our CTO Alexander. And in this case I would use first three harmonics. Will have mesh deformation included, geometric nonlinearity, and also pre-stress included in this case. So let's move on to the product itself. So here I've built the geometry already. So you can see two plates separated by air gap. I will show you how this can be built. For example, in this case I also tried to take advantage of shared expressions. So this means that we can define the geometry. um, so basically length, um, here 1000 micrometers, width, and thickness of one of these plates, and the air gap, frequency and voltage. And I could parameterize my geometry based on these dimensions, as you can see here. And yeah, once I have the geometry, then I could define different materials. So for example, here I've chosen air from the materials library and also the monocrystalline silicon. One thing to highlight here is we can easily do anisotropic material properties. For example, here elasticity matrix for silicon, because this is monocrystalline, and for this there is strong anisotropy expected. Then I can define several regions which are interest or which are required for defining the interactions or boundary conditions. These are not necessary, but helps in some way to tagging the domains with some physically meaningful name. Uh, yeah, once that properties are defined, this is the this is the part, or this is the menu where we define different kinds of physics here, excuse me. So in this case, we have four kinds of physics involved, or four types of physical processes involved. First is laminar flow, which is in the air gap. Then solid mechanics, which takes care of the deformation of the top plate here. Then electrostatics, which is uh, supplying the force, so uh, having the voltage across the gap produces the electrostatic force acting on the top plate. Then mesh deformation, because the mesh, so as the top plate deforms, so the domain or the air gap has to be squeezed, and we have to tackle the mesh deformation there. So let's go through one by one these physics and how they are coupled. So laminar flow, we have to define the no slip boundary conditions for the boundaries where we expect the flow to be static. So these are the so basically we can just try to hide some regions here. So as you can see, uh, so on the bottom I have assumed that there is no air gap, so that's why there is the no slip boundary condition on the bottom plate, which is static, also no slip, and this is on the side of clamp. So three boundaries chosen as the no slip boundaries. And yeah, and outlet, so this is the outlet where the air should move in and out. Then beam wall is the wall where basically that's the that's the boundary which will be interacting with the air. So this is the moving boundary basically. And the symmetry, so symmetry on this side, because we don't want to simulate the whole domain in this case. Then let's move on to solid mechanics. So we need to clamp one of the uh, uh, one of the sides here, so as you can see here, then clamping the bottom plate. Then the way the electrostatic force is applied, and yeah, the large displacement that is included for the mesh deformation in this case. um, Before I go to electric force, maybe to include the electrostatics. So in this case it's very simple to apply the voltage. You select the volume, so target plate in this case, which I have already defined here as electrode target and the ground target, and these are basically chosen here. And on top plate I apply the cosinusoidal voltage with some amplitude, and set the ground to 0. And once this is done, you can select from here the electrostatic force as the interaction between solid and electrostatics, and that applies the force on the top plate. And for the mesh deformation, we apply we include this as a physical process, and apply the constraints on the solid domain, that the solid should move along with the mesh. I haven't described how we couple the laminar and solid mechanics. We'll describe in later in the script mode. Yeah, so let's move on to simulations. So in this case, we can create several. So in this case, we have to first create the mesh. We have to highlight this here. So we have structured mesh are available for these kind of simple geometries. You can easily create such nice rectangular mesh. And yeah, let's move on to simulation. So there are several simulations I have already run, and I would like to focus on one of them. So I chose one of the case from the paper which has voltage of 31.7. There is no reason for choosing, just chose one of these and tried to simulate it. Chose the analysis type as multi-harmonic. As you can see, four types of physical processes. uh, Frequency defined in the shared expressions, so that is easy to do frequency sweep. And as Alexandra described, the harmonic. So first harmonic, 2 and 3 are these harmonics at the first fundamental frequency, and the 4 and 5 at the second, or twice the fundamental frequencies. um, yeah, and ran this on 48 cores. and so on. So let's try to first look at the script. For this case, I had to add some additional measures. So we- to for example, to describe the or to tackle the mesh deformation in this case. So I got the auto generated script first, and then I could add simply a few expressions which we need for mesh deformation. So before I go into those, let's have a look at what's the idea behind that. So in this case, to tackle the mesh deformation, I take an example of electrostatics. So as you can see, the weak formulation here, the first equation, there is gradient of electric potential. Uh, uh, it has been integrated once, so that's why you see yeah, grad of electric potential and the electric permittivity in this case. And you can see the star, which means that this is on the deformed domain, as you can see on the right hand side, and we have to bring it to the undeformed domain uh, by using some Jacobian transformation. So in this case, as you can see here, the from going from the undeformed domain to deformed domain, we have to use Jacobian transformation, and inverse is also shown here. So if we do this mathematically, you end up with the expression or the equation at the bottom here, where the gradient introduces inverse of Jacobian, and the because of the volume integration, you have this determinant of Jacobian involved here. And once we understand, we have these equations, we can go back to our script. We have to define additional field which was already defined when I introduced the mesh deformation physics. And what I have to do here is to calculate the Jacobian like this. So simply take the gradient of the deformation with respect to um, the physical space, and then compute the inverse. It's just function, you can use inverse of Jacobian and the determinant of Jacobian. Once I have this, I can uh, go through the equations, and for example, I can compute grad v simply by grad v times J inverse, and transpose operations are done to take care of those mathematical transformation. Yeah, and similarly, I mean, these operations have to be done for the laminar flow as well, which have been added here, not to scare you away, but yeah. So this is not that complicated as it looks like. And let me go to the electrostatics example. So yeah, so as you can see, I have defined here the first grad, which is the degrees, so unknown variable, and the second is for the test function of the electric potential, and we can simply add this integral, which is grad of v times grad t test function v, and multiplied by determinant for volume integral. And that's all for the electrostatics example. Yeah, not that's not all. We have to also do for electrostatic force here, but yeah, I won't go through details of that. Another thing I wanted to explain here was the coupling between the laminar flow and the solid mechanics. So in this case, we implement this by enforcing the velocity at the interface to be the time derivative of the displacement. And as we enforce this boundary condition, we naturally get the force balance between the solid mechanics and solid domain and the fluid domain. And this is added by these two lines. In addition to that, as I said, we also include geometric nonlinearity and pre-stress. So it's easy to add pre-stress here. We just define two lines of code, and um, yeah, we have to include the pre-stress as the argument, and that's it. And once we have done all of that, the last thing, which is auto generated, is to tackle the deformation of the mesh itself. So as we deform the mesh, so the node are redistributed smoothly using a Laplace solve for the mesh deformation field in this using this. So this wasn't added by me, this was auto generated. And yeah, once that is done, we are ready to solve. And yeah, as we solve the, I have here pre-solved example, and you can take a look at logs. We have 800,000 degrees of freedom, and it takes about 15 iterations to solve, and about 1,000 seconds. So that's about 15 to 16 minutes, I guess. And yeah, once we have the solution, let's look at the results now. So that's how the results look like. So I exported the time, so I extracted, so the result that we get, simulation results, we get harmonics, and we have predefined functions to export this as a transient, let's say um, transient files. And that's what I have visualized here. So the top plate, which is deforming harmonically, and as it deforms, it squeezes the air between, and you can see on the bottom left is the section at the center of this plate, and you can see the flow moving in and out. And this was done for frequency of 100 hertz, 800,000 degrees of freedom, took about 30 minutes on 12 cores, and full this includes all physics fully coupled, and yeah, electrostatics, solid mechanics, and fluid dynamics. That's the qualitative comparison. Let's have a look at the quantitative comparison. So here what I plot is the displacement, normalized displacement along the center of the plate, so going from left to right here in the center of the top plate, uh, only until the only because we did symmetric example, so that's why it's cut at 500 micrometers. And here you can see the orange plot from the paper, which is measured data, and on top of that is blue curve, which is from the Quanscient Allsolve. We can see that the displacement is slightly over predicted, but that could just be because of the mesh, or yeah, because I didn't use sufficiently fine mesh probably. So yeah, I mean, this we would consider a reasonable match in this case. um, yeah, so that's all from my side. I would hand over to Yuka. um,
Yes, indeed. And actually, yeah, thanks, Abhishek, for that. And now, since we have 30 minutes or so left, I think it's time for the Q&A section. So, Abhishek, you can come right back, and we can also invite Alex to the screen. And yeah, we saw there were already some comments in there, where some rather questions and some answers. So maybe each can go through the already answered questions from the comment sections. But in case there are any new questions, please use the chat, and we'll answer them here live. Mm, Maybe we can start with a question on the scripting. So as we saw in Abhishek, your example, you had to use the Python scripting interface. Is that part of every simulation? So do you always have to use the scripting interface when implementing the harmonic balance?
uh, no, no and yes. So for this case, we had to use scripting, as Alexander showed. For the joule heating, it wasn't the case, but for this case, we had to include mesh deformation, and that's the reason I had to additionally implement this in the scripting. But in future, we are going to include that also in the GUI, so there should be no problem in the very near future. But that also highlights the uh, advantage, or the power of Python scripting. So if you want to do something non-standard, it's quite, or I won't say easy, but it's relatively easy to implement if you know the equations in your uh, finite element weak form.
And one thing to comment on this, we're soon releasing our API for remote access. And of course, in the case of API, if you're going to do automated runs, then the setup is only to be done once. But as Abhishek said, it's only for the cases where you have mesh deformation that this is needed for now. But this is not a fatality. This can be also automated. I see, Jukka, how difficult is it to mesh complicated real structures? Well, it depends what you mean. If you mean like thin layers with MEMS or like complicated structures like big mechanical assemblies, we can deal with both. So you can import a step file or GDS files. And basically, if you have drill holes or fillets, we have a special measure that handles this really well. This is for the mechanical assembly side, so complicated geometries, yes, it's FEM, so any geometry works, and we mesh it with hexahedra, pyramids, prism, and tetrahedra, so anything really works. For regarding MEMS devices where you have thin layers, this can be really a tough time if you have a lot of thin layers and you have to transition between two different meshes across different layers. We have a specifically made tool for that basically collapses all the layers to a shared footprint and meshes that in 2D and extrudes from there, which makes it basically the best possible quality mesh because it's extruded across all layer and it just works in all cases. And you don't end up with weird shaped tetrahedra because the software tries to match two layers across a few hundreds of nanometers. So these two cases are covered. So I would say it's not that difficult.
All right. There was a question before the event from one of the attendees, a more general question on, is there ways to couple external circuits?
Yes. So RLC components are supported. I don't know, Abhishek, if you had any, but at least what I did was driving a current in. And at what we call these lumped interaction, you have access to always the voltage and the current, or, well, basically, depending on the physics you're simulating, you have access to this and that, or this and that. But if you do current flow, then you're going to have access to the voltage and the current at the electrode. And basically, you can do anything with those. So you can make a relation between the voltage and the current and the time derivative, which allows you to very trivially couple RLC circuits, lumped RLC circuits to the simulation. And this just trivially works without any effort. Also with the harmonic balance and all sorts of analysis we're providing.
All right. There was a question about mesh imports. So can you import mesh from other programs?
Maybe I can answer that. So yes, we can import at the moment from Gmesh, and relatively soon we would be able to import the Nastran files. So that's the two formats that we support at the moment for the mesh import.
The mesh import is actually streamlined in the same way as you would have a step file. You will import your mesh, it will detect all the surfaces, edges, and points, and you can do the whole graphical process based on the mesh that you have imported. So pretty powerful feature.
All right. Then answer question on material nonlinearity. So can we handle contact and material nonlinearities with Quanscient
Yes.
also?
So contact, yes, we have actually we even made some LinkedIn posts regarding contact using the mortar finite element method. Yes, we have done actually even CMUT ultrasound membranes with electrostatic force in contacts, also including mesh layers between the two contacting pairs. We've done pretty nice things regarding this. What we have not yet explored too much is the material nonlinearity. So we are working with some people who work on plastic deformation. So our solver can handle this, but we're not offering that in the graphical interface right now for sure. And regarding hyperelastic materials, this is also not something we put a lot of focus on, but like it is classical finite element formulation. So that should definitely work easily if you know the equation in the scripting interface. And again, this would also work with the harmonic balance method, with the harmonic method, no, well, transient analysis as well, just out of the box without any effort, except for the parts that Abhishek mentioned regarding the mesh deformation.
Right. Next question. Is it possible to automate the geometry modeling process by code? Which kind of file can be uploaded to represent areas or volumes?
Yeah, maybe I can say something about that. In principle, yes. So you can automate the geometric modeling, like I showed you with the shared expressions. That's one option. There are some of users which use even more advanced techniques, like using Python interface to Gmesh. So that's one of the other options. And with API, if I'm not wrong, it should be even easier in that case. And the kind of file, so we support at the moment step and GDS for file formats. So the step file can any CAD software can export that, and the GDS is particularly supported for the MEMS community. Yeah.
Anything you want to add, Alex?
No, I was looking at the next question from Anton.
Yes.
Yeah, that is a very good question. So, is it possible to edit and run the scripts from external editors? I think the closest we'll provide soon is the API, and once the API is there, basically you throw to our servers the required files, including the Python script, and you're pretty free to do anything you want in terms of automation of the workflow. So I hope that answers the question. But basically, yes, you could do this with the API that's coming out soon. I don't know if Abhishek, you feel that's answering the question to
Yeah,
the extent expected.
I think so. Yeah, nothing new to add.
I think the final question we can answer, again, a more general question regarding MEMS is, well, rather specific. So, do we support piezoelectric materials?
Well, yes, like piezoelectric is a really trivial one for us, as we can just solve all the equations together. We don't have these issues of gluing two different pieces of software together. Our solver is a generalistic PDE weak form finite element solver built entirely in-house. And so in that sense, we don't have restrictions regarding classical issues of piezoelectricity simulation or acoustic structure interaction simulations. That's really, you might have a hard time solving this when you try to couple different packages together.
All right. I think that ends the Q&A section. We still have a couple minutes. So, yeah, this point, I'd like to thank Abhishek and Alexander for your wonderful demonstrations. And of course, all of you participants here for the wonderful questions. So to quickly recap, in what we saw today, we learned what the harmonic balance method is. We learned some theory behind how it works and saw its application in 3 use cases. And the results of these being faster runtime and basically more straightforward simulation setups. In addition, you got a glimpse to our product, Quanscient Allsolve, and what kind of benefits it can provide, especially in the field of MEMS simulations. Those would be namely the utilization of cloud computing, meaning more computing power and RAM, enabling, for example, hundreds of parallel simulations with zero added computational time. And overall, the flexibility provided by the unlimited number of licenses or a lack of licenses altogether, however you want to think about it, the browser-based nature requiring zero hardware downloads, and the usage-based pricing. All in all, if you want to get in touch with us to see how the harmonic balance feature could enhance your MEMS simulations or are interested in the other benefits, you can read more and schedule a 30-minute introductory call at quanscient.com/allsolve. In any case, thank you once again for joining us today, and hopefully got what you came here for, and we'll see you again. Bye now.